All right, let's look at another one. This is going to be a two-step pulley. Okay. So a two-step pulley. All right, let's give this pulley system, remember, two different strings, two different masses. We're going to mass some things out. Now, I can make this two-step pulley by putting two different discs together with infinitely super duper glue. So there's no slipping between the two discs. So imagine two discs stacked on top of each other. So this disc right here, the big one, the large disc has a mass of 60 grams. The mass of the small one is 20 grams. The radius of the large one is 30 centimeters. The radius of the small disc would be 15 centimeters. We're going to call this block 1 and this block 2. The mass of block 1 would be 1 kilogram, and the mass of block 2 is 3 kilograms. What is the angular acceleration of the system and the tension each cord? So, same thing we've done before. Block 1, FT1, FG1. Block 2, FT2, FG2. Now we've got this two-step pulley business. And we've got an FT1 on the small radius, and we have the FT2 on the large radius. We could add in a normal force from the pivot point and the weight of the pulley, but we're not going to need that for this problem, so we'll just leave it out of our picture for now. Then we sum the forces, just like we've done before. So let's sum the forces in the y direction. It would be M1, A1. They have different accelerations because each wheel, as it makes 2 pi radians, each string is going to go 2 pi times r. So the big string, or the big radius, is going to have a bigger distance than the smaller radius, but they're both going to move for the same amount of time. So one's going to have a bigger acceleration than the other one. So because they're at different radii, they have different accelerations. They have different circumference. The string will move a different distance. That's what gives it mechanical advantage. All right. So then FT1. Oh, what do you think? Let's go back and make our prediction. What do you think the system's going to do? Almost forgot. All right. So Namisha thinks one's going to go up. They are, but it's okay. You think one's going to go up, and so then 2 needs to go down. And then the rotation would have to be clockwise. There's nothing wrong with that. If we are incorrect and we get the right, we'll get the right answer, but with the wrong direction. Yeah, because we thought everything was moving one direction. You get the, and you get the answer, and it's like, oh, you think it's positive, but it's actually the opposite direction. Look at the negative sign. So far, we've been correct with all of our guesses. I guess I should purposely do one wrong one day so that you'll see that you'll get the right number, just wrong sign. All right, so so then let's go back to summing forces now that we know which way is up. So minus FG1 is equal to M1A1. Doing the same thing for block 2. So then FG2 minus FT2 would be equal to M2A2. And for our torques, I'm just going to come right down here. Our torque would be equal to I times alpha. And in this case, we're looking for alpha, so it's the key. I'm sorry for that spastic move there. Okay, if we think it's going clockwise, then FT2 times R large, I don't know, minus FT1, but it's at a distance of R small, is equal to I alpha. All right, same thing we've done before. We solve for FT2, we solve for FT1, we stick it back in here. The thing is, we want to solve for alpha, so we're going to make a substitution because A is equal to R alpha. We'll make this substitution in for A1 and A2, and we'll be able to solve for alpha. So FT2 would be equal to, all right, so then FT2 would be equal to FG2 minus M2A. FT1, we've done this so many times today, would be FG1 minus M1A. We're going to stick that into our torque equation. So just don't forget to multiply by R large. So FG2 minus M2A all times R large minus, I'm going to use a parentheses to make it look like a big deal. FG1 minus M1. Whoops, that's a 1 and that's a 2. That's a 2 M2. There we go. And then times R small is equal to I times alpha. It is A1. I just got real excited about R2D2 A1 sauce or something. I don't know. Steak. I don't know. All right, so here we go. M2G R large minus M2 A would be R large times alpha, so R large squared alpha. Woo! Minus M1G R small All right, so fixing that sign error there. Okay, so then that would be negative M1. A1 would be R small alpha times R small. So that would be R small squared alpha is equal to...
Pardon the interruption. I have 2 announcements.
We can do it. All right, it was a disc, but it's a crazy disc. It's a disc made of 2 things. It's a disc made of a big guy and a little guy. So we'll have to have 1/2 mass small R small squared. Are you with me? Oh my gosh, it's getting so complicated. Plus 1/2 mass large R large squared. All times they will have the same angular acceleration because they go through the same angle change over the same amount of time. So, oh my goodness. Now, it gets to be so super duper fun here. And what it's going to look like is that we have our M2G R large minus our M1G R small will be equal to 1/2 M small R small squared plus 1/2 M large R large squared and then we're going to add to it our M2 R large squared and our M1 R small squared. That was from the other side. And I factored out their alphas all together. Boom. And holy cow, this looks like, I can't make it small, but look. This looks like torque. Force times R minus force times R is equal to I. Look, this is the moment of inertia of the little disc, the moment of inertia of the large disc, and these are the moments of inertia of the point mass. Okay? So it winds up having like the same sort of shape to it as far as like what the equation looks like. And once you do all of your substitution, you're going to get alpha is equal to 25 radians per second. Plus a little bit, it was 25 rounded. And then after you find that, can you find the acceleration of each? A is equal to R large alpha. That would be A2. And A1 would be R small alpha. So R large was like 0.3 times 25. And A1 so this one will be like 3.75 meters per second squared. And this one's going to be like 7.5 meters per second squared. And then we can substitute and find FT1, which is going to be an exercise for the student. And an FT2, but I have found all the bits and pieces for you. Boom!